Um, Thanks for coming, everybody. Um, so we didn't have a Twitch stream last week, um, but I spent the time, hopefully being productive, and uploaded all of the previous streams to YouTube. And one or two of them I had to glue them together. And actually, what helped me most with that is that I got one of those new fancy MacBooks, the M1s. And so running Final Cut Pro and stitching together those videos actually went super fast, and it was way more pleasant than I've previously done on my previous MacBook, where it would just take quite a long time and be really slow and sluggish. So that was kind of cool. But they're all there now, and if you want to see the archive of these sessions, you can go to the Shuffle Sharding channel on YouTube. Just search for it, or go to my website shufflesharding.com and click on the YouTube icon, or click on videos. And either way, should be pretty easy to find them. It's interesting. The views on YouTube track pretty well what the viewership on Twitch was, which I find super interesting. DNS again still has the most views, which is cool, and the view order, the number of viewers is not like just the order I uploaded them in or anything like that. But seems to kind of organically match like the numbers of viewers we got here on Twitch, which is kind of cool. Now we get more viewers on Twitch. Typically the talks get 1,000+ views on Twitch. Maybe that's because they're more recent, or it's more discoverable or something, or maybe just Twitch is better than YouTube. I don't know, but on YouTube they're still getting interest. Anyway, if you're looking for any content, that's where it is now. So that's now done. And this one, hopefully, now that I have that MacBook, I'll just upload this right away. Once we're done, and hopefully I won't need to edit it or anything. I'll just get it right up. So that'll be nice and easy. As usual, if you've got comments, questions, whatever, put them in the chat. We'll try to get to them while we're talking, or at the very least right at the end. I always do a scan and try to address anything that hasn't been covered. There are no dumb questions ever, and happy to go over things again if we need to, and happy to get down into any level of detail to help folks understand. We're going to talk about idempotency today. But before I get that, I should also just say I'll be at AWS reInvent in person in about whenever that is, 3 weeks time. Oh my god, it's soon. I think I'm probably going to do one of these streams from reInvent, because why not? So that might be a bit different and special. And if people have ideas for what topic to cover there, let me know. But all right, we'll dive into idempotency. I asked folks on Twitter yesterday about 3 topics. What would they like? Sci Guy, you missed my intro. They're all on YouTube now. Just go to the Shuffle Sharding channel on YouTube. They're all there. Everything's uploaded. And I asked folks out of 3 topics what would they like me to cover. And the first topic was shuffle sharding, which I will cover at some point, and hopefully it will be interesting, but that got the least votes, even though I know people have been asking for it here in the chat, and we will get to it, I promise. The next most voted topic was meetings, and how to not suck at meetings, which I still suck at meetings, but I suck less at meetings, I think, than I did So what kind of soft skills we can use to make meetings more effective, because I know a lot of people hate meetings. So but we'll cover that as well someday. But the one that won is what we're going to talk about today, which is idempotency, which my dictionary and my spell checker tells me is not even a word. Yeah, when I type it into Twitter or MS Word or pretty much anything, I get the little squiggly lines under this word telling me it's a misspelling, and they have the word idempotent, right? But they don't have idempotence or idempotency, and so I actually don't know which is fully correct. Is it idempotence or is it idempotency? But I've always heard it as idempotency. That's just what I've always heard, and so that's what I'm going to use. And I've also heard people say idempotence or idempotency, right? Okay, I say idempotence or idempotency, and I think those are equally valid too. I don't think there's one true way to either spell or say this word. So already we're off to a complicated beginning. But idempotency can be a really intimidating thing. I remember first kind of even hearing the word in the context of the HTTP RFCs, right? So the protocol that the web uses, Hypertext Transport Protocol, that that's what your web browser is using to talk to a web server. The standard for that is an RFC, right, maintained by by a working group at the IETF. And if you're ever working on a HTTP in low level, you'll look at that RFC, and actually other related RFCs too, that go into this topic in detail. They've got big long sections about idempotency and how to handle it. And I remember being really intimidated by that. It seemed like a very academic term, and it seemed I just couldn't get my head fully around it at first. And it seemed maybe overly complicated. I was kind of thinking like, wow, for what this is supposed to solve, there's an awful lot of detail here. Does that seem right? And 20 years later, I think it is right. And actually the amount of detail that's in the HTTP RFC is actually kind of a rare, really good example of just how much detail it takes to wrangle idempotency. So it's a naturally intimidating, a naturally complicated topic, but it's also a great place to begin in distributed systems engineering, and it's also a great place to get started because it's simpler than it seems, at least to start with. So let's dive in. So we've talked a lot about the word. What is the basics of what idempotency is, right? So at the core, right, one way to think about idempotency is it's a property that lets you retry requests, right? So you make a request, let's call that R1, and you throw it to some system, and that request could be almost anything. It could be like, I want to buy this physical good, like let's say I'm buying something on Amazon, right? Or it could be I just want to check the balance in my bank account, or I just want to read a web page, or it could be something where you're uploading to Dropbox, say, right? And for all sorts of reasons, that request might not succeed, right? So you want to be able to retry it, right? Let's call that R2 is the retry, right? And idempotency at its core is just a property of like what we're going to do in our system to make sure that when you do this, you don't just end up with like basically two things. Like imagine you're uploading a document to Dropbox and it doesn't work, and then you have to retry. Okay, great, but now you've got two documents, right? That's not what we want. That's not an idempotent design. That doesn't have idempotency in it. And it can have small side effects like, oh, now I've got two documents and I have to clean it up, or two documents and I don't notice and now I'm getting charged for two instead of one, or whatever, right? Those can be minor things, or it can have really big consequences, right? Like idempotency issues can really break open systems in serious ways sometimes, and trigger all sorts of transactional incorrectness in those systems. So that's why we pay attention to those details. But that's all idempotency is, right? It's just like the goal or target of like, look, I want to be able to retry things, and when I retry them, it's like the first time worked, and it's not like there's no risk of a double or triple or multiple action, right? And that's important in distributed systems for a few reasons. One is from like just a basic availability perspective. Systems fail, and it's not always clear how or when they failed, right? And we have to be able to retry anyway and still get to a correct state. I'll go into an example of that in detail. But also in a security context, right? Like a kind of attack that an attacker can try to do is a replay attack, right? Where sometimes they can try to trigger your client to make retries, or they can just grab your message or your request, and even when it's encrypted, sometimes they can just send it again, because it's not like they're trying to break the encryption, right? It's not like they're trying to understand what's in the request. They're just trying to send it again, right? And in a lot of systems, if they're not defensive of that, there could be bad consequences, right? Because somebody malicious could come along and just try to replay requests and mess with the overall state of the system. So let's drill into like what's going on when things fail and why we actually need to even retry in the first place. Because that's we're really going to learn, like just in going through that, we're going to learn literally the most important things about distributed systems. They really are very simple at the base. At the core of distributed systems engineering, right, there's a famous quote which I can't quite remember perfectly about, a distributed system is really any system where somebody else's computer, could break me, right? And that's very true. But like, the simplest distributed systems always have at least two components, right? Otherwise, they're not distributed. And so let's say we've got a client and a server, right? And they're they're distributed, so they're in different locations, and that can mean they're like on different sides of the world with like many tens of milliseconds of latency between them, or it can mean they're like right beside each other, maybe in the same rack, right? But they're still a distributed system. They're not the same system. And there's some medium of communication between them, right? So in our context, typically that's the internet protocol, right? Like IP, right? But they've got some way to talk to one another, right? And so in our model here where we were talking about requests, what that looks like in the system, right, is the client is making the request, right? So it's sending R1. And now let's say this request failed, right? From the client's perspective, right? Let's say the client never gets to the point where this request is completed and has a 200 OK response, if this is HTTP or whatever, that says, this request succeeded. So let's say this is a failed request from the client's perspective. Well, there's a few reasons that could be, right? So one reason is the request just never even made it to the server, right? It just got like dropped somewhere along the way, or there was some kind of transient problem, who knows, right? Like some network buffer filled up or whatever, right? And the request just never made it to the server. So that's one way it could fail, right? And maybe, and this request will just like time out from the client's perspective, typically, right? Another way is that it did make it to the server, right? And as far as the server is concerned, everything went fine. Got the request, did what it needed to do, and sent the, I acknowledge this went okay, here's an okay response, have at it. But that response is what got dropped, right? So this response never makes it to the client, right? And those two scenarios from the client's perspective look the same, right? Either way, the client gets a timeout, they never get a 200 OK, they've no idea whether that request really happened or not, right? All they know is, I never got the acknowledgement, right? And so in the second case, at least, where the server did get the request and carried out some action, but the response didn't make it to the client, like that's an example of a partition, right? And all a partition means, really, it's just a fancy way of saying, look, in our distributed system, we've got like two different perspectives and they don't agree with each other, right? Like the client doesn't know whether the request happened. As far as it's concerned, it got this timeout, there was an error. The server knows it happened, right? Because it got the request, it processed it. So they've just got different views of reality, right? Like on this, and let's say this request was to change the value of something, right? Let's say it was, putting $10 in my bank account, right? Well, now the server thinks your bank account has an extra $10 in it, but the client doesn't know whether that's true or not yet, right? So it's another kind of reflection of the partition. And there's no like one correct perspective either. Like it's like if you're on this side of the partition and you can't reach the server, like it might as well be true that the request never made it there and it's not $10 more yet. But if you're on the server side of the partition, you know the $10 made it in and it is there, right? Those are equally valid perspectives, right? Which is like a really important concept to get into your mind. And that kind of blew my mind the first time I learned it. I remember it very well. I was working at a company called HEANet in Ireland, and I was there as an intern at first, and my mentor there, Anna Wilson, was walking me through how like BGP works, which is a network routing protocol. And again, that is a protocol that seemed very complicated. But she explained to me how like, yeah, but what you're forgetting is different networks can have different perspectives and they're all true, right? And so being able to wrangle that and being able to think about all of those equally valid states at the same time, like that's kind of why distributed systems is hard, right? And it's kind of why we have to come up with techniques like idempotency to make it easier, right? And to solve those problems. There's another extreme example of that. When I was working on our health check system for Amazon Route 53, our DNS service, we would have customers ask us consistently, hey, I need that health check to tell me whether the system is up or down. And we're like, okay, but it's not quite that simple. I know it sounds like a very simple ask, and I agree with you, but it's not always that simple. And one reason it's not that simple is, okay, well, we've got health checkers spread all over the world, in every AWS region, right? And they're hitting the targets that are configured by customers. And some of those targets are going to be in the same region as some of the health checkers, right? And so if there's some kind of problem with the internet, well, as far as those health checkers are concerned, like let's say a health checker in Dublin that's checking a target in Dublin, it's going to go, yeah, it's healthy, it's great, it's up, everything's good, right? But if there's some kind of internet problem around Dublin, right, and nothing else can see Dublin, everything else is going to go, well, but it's down, right? And those are both true perspectives. Everything outside of Dublin thinking it's down is true for everything outside Dublin, and everything inside Dublin thinking it's up is correct. And then there's an opposite perspective that's also true. Like the things that are in Dublin are basically going to think the entire rest of the internet's down, right? They're going to be like, yeah, every AWS region is, failing its health checks or something like that, right? From the perspective of being like inside the minority partition, right? And that's all true at the same time. Now, in reality, we just don't really have partitions like that, right? Like we have a very reliable AWS backbone connecting all the AWS regions and all the rest, right? But in like a mathematical or academic sense, that is how you have to model it and how you have to think about it. And getting used to this idea that there are parallel states that can be true at the same time is an important concept for wrangling distributed systems. Now, after I learned this from Anna, a more general more general statement of these kind of properties, eventually became known as the CAP theorem, right? Which you can search for the paper. I don't know. I should have printed a copy here that we could have looked at. And the CAP theorem states, and we'll probably do a separate Twitch stream on the CAP theorem someday. The CAP theorem, all it states is that any distributed system like this, anything that's got multiple nodes and anything that has mediums of communication between those nodes basically can't be consistent, highly available, and partition tolerant at the same time. You just can't have all of those things, right? And there's lots of ways to see it, and we'll go through that in a separate stream someday. In fact, there's refinements on this. The reality, like that sounds like, well, you have to sacrifice one of these things. Like let's sacrifice, say, consistency, right? And say, well, we're going to have high availability at any given time. Either side of the partition is always going to tell you what the value of something is, so that's highly available, and it's gonna withstand partitions, just like this system is. They can't communicate, but like the client can still tell you what the value is, or the server could still tell you what the value is, but they won't be consistent because they'll tell you different values, right? Sorry, I muted there to cough. I have to cough every so often. I've had a head cold, but I'm coming way out of it. And I took COVID tests, and I do not have COVID. Even my PCR test says I don't, so that's good. I'll take a drink. Now, it can look like the CAP theorem lets you sacrifice any of those. Like I just showed you how to trade off consistency to get availability and partition tolerance. But the reality is it doesn't really work like that. You can basically have PA together, like partition tolerance and availability, or else you can have consistency. That's pretty much the only way you can arrange things, which is referred to as PAC-ELK, which I see Lulu put in the comments. So that's that's right. But we'll get into that deeper some other day. But for now, all that matters is, right, client makes a request. It cannot tell the difference between that request may have succeeded and I just didn't get the acknowledgement, or the request never even made it there. So the server never did something. So when you're doing a retry, right, when OR2 comes along, there have to be special things about OR2 or the overall design of the system that indicate, well, if you're in the second case where the request was processed, right, the server has to know, well, not to do it again, basically, right? Or to do it again in a way where it doesn't change any state, which is another option. We'll get into both. But either way, effectively, at the end of this sequence, whether OR1 succeeded or not, and then we send OR2, like the end effect has to be the same. The systems have to be in the same state for this system to be idempotent. Right? That's what it is. That's the core of this. And so we'll cover a bunch of different techniques for how to achieve this, and for how hard it can be to achieve, and some of the wrinkles. I should say we have an Amazon Builders Library article about this that my colleague Malcolm wrote. It gets into really great detail too, and covers a lot of strategies that are super interesting. All right, so let's talk about strategies, right? So the first thing you could do is, okay, well, let's look at it. So when a request comes in, right, and it gets to the server, and it's processed, that's good. But then when it's repeated, actually I'm going to call this OR1 prime instead of OR2, just to make really clear that they're basically the same request, just being retried. The server needs some way to basically tell, look, these requests are this is the same request I saw before. So you don't need to do it again. You don't need to carry out those actions again, right? And there's a few ways to do that, right? So one is you could just look at, you could try to give the request some kind of fingerprint, right? And it's tempting in systems to go, well, let's just look at the parameters of the request, right? Let's say we've got some simple API, and it's I'll make it a put just to be more pedantic. So let's say it's a put request. So we're sending an object into a server, right? And we're going to say, okay, well, let's say it goes to my object, 111, blah blah blah, and then there's some like content in here, right? And you could just fingerprint this whole request, right? You could just like use a checksum algorithm, a hashing algorithm, to like give that a synthesized kind of fingerprint. Like here's a synthetic fingerprint for the whole request. And when that gets to the server can actually do that fingerprinting. Like you don't even have to modify the protocol to do that. And it could just say, okay, well, when I get this request, I'm obviously going to do everything the request wants me to do. And alongside that, I'm going to record, in some kind of durable data store, the fingerprint of the request so that I know it happened again. So that I know it happened, right? So it stores the fingerprint, right? And that can work in some systems, but the classic challenge with this, right, is okay, but like let's say I change the object back, like intentionally, to something else, and then I want to set it to this again. Okay, well now my fingerprint would stop that from working, right? So if you're synthesizing the fingerprint from the request itself, you run into trouble super fast. Like it's really, really hard to make that work for protocols in practice. Although I've seen a bunch try, right? So you lead to this problem of like ABA problem. Like what happens if I make request A, then request B where I change it, but then I want to make request A again, and that's totally legitimate, which is a super common pattern. All sorts of protocols let you do that. But if you just have this naive, well, remember every request you've ever seen, give it a fingerprint, and don't let it be repeated, that won't work. This technique of like giving requests a fingerprint and like maintaining a record of the ones you've seen and then rejecting ones you've previously seen is also called a strike register. That is, you maintain a register and you strike things in the register when you see them. And if you see them again, you don't let them happen again. And it can be a pretty crude solution that you can bolt on to protocols that didn't think about idempotency. But it's not great. And you run into this, like I keep saying, ABA request problem. So it's pretty clear you actually need something in the request itself that's going to be an identifier, right? You need something that the client actually comes up with that says, like, here's my actual unique ID for this request, right? And so, in the parameters of the request, you've got some piece of metadata, typically in a HTTP header, if it's like a REST protocol or whatever, where you put a GUID, right? Like a globally unique ID. And hopefully you just use something like a regular GUID library to come up with that, right? It's okay. I'm just gonna don't know what to do with that comment, but they put a GUID in the request, and there's not much more the client has to think about, right? It just has to create a GUID when it's creating the first request, and just put it in there, and it can send that to the server, right? And now the server goes, okay, well, if I see that GUID again, I'm not gonna reprocess the request, right? I don't need to think about that too much. But the next kind of challenge that runs into, though, right? The natural kind of thing is like, okay, but what if they're clever? What if they try to mess with my system and they don't use like truly random GUIDs, or they try to collide with existing GUIDs? And the answer to that is, for the most part, it doesn't matter. For the most part, a person can really only impact themselves, right? Like, if an attacker who was trying to do that, they wouldn't know the other GUIDs that other clients have used. GUIDs should be huge, basically random strings, and if you use a good GUID library, it'll do that for you. They're in a very large, unpredictable space, so just trying to guess them won't work. So they really can't victimize anybody else. And yeah, they could victimize themselves. Like, they could make request A with GUID A, and then they could make different request B but reuse the GUID. There's not much, not much harm caused by that. They're just making their own first request not get, or they're making their own second request not get processed. So it turns out when you threat model it, it's not that big a deal. Someone's asking, does this not need a huge amount of storage for all the GUIDs? Yeah, you got to record all the GUIDs. Typically, it's not a huge amount of storage. I mean, in the context of like things like an object store, or the kinds of requests that are like launching an EC2 instance, say, or something like that. Like storing a GUID is not a big deal. Lost my pen, but but yeah, you do have to do it. And so this is like the normal, like approach. Is this a single point of failure? Not really. I mean, how you store the GUIDs in a data store is the same as storing anything else in a data store. That data store itself can be distributed, sharded, all the usual things. So it's not necessarily, can be redundant and resilient. It's not introducing a single point of failure. But this is the general, like, how it's solved, right? The client comes up with a GUID. Sometimes these are called idempotency tokens, right? It accompanies the request, and then when the server gets it, it's like, okay, that GUID, I'm going to record that GUID in my, ACID data store of some kind, and then whenever a request comes in again with its own GUID, I'm going to see if I have that GUID already. And if I do, I'm not going to carry out the actions of the request, right? So the next kind of little piece of detail is, okay, now we want the requests to be idempotent, which means we want the client to experience normality as much as possible. And so I've seen a bunch of protocols get this wrong, where what they do is, okay, well, when I detect a duplicate request, they return some kind of error, right? So the server detects, okay, yeah, I've seen this GUID before. Here, dear client, you sent me a duplicate request. Okay. And what's the client supposed to do with that? Right? Well, now the client knows its action occurred. Great. But if there were anything in the response that they needed, they don't have the response. They got an error, right? So a lot of protocols, there's meaningful things in the response. Like maybe I upload an object and it returns back a response that tells me, here's the impact of that object on your quota, or here's the directory we put it in, or something like that, And now it has to go maybe read the object to get back that response again, right? So you're forcing the client to do this dance of extra requests. So our pattern in general is actually, if it comes in with a duplicate GUID, okay, we're not going to write it again. We're not going to carry out the actions, but we're going to give it the same response the first request got. We're just going to give it the same response, right? Like, here's your 200 okay. Here's your response, right? And that just makes clients easier to write. It just makes the overall system simpler, right? That's all that's about. But it is a nice little saver. Now, the HTTP protocol, which I mentioned earlier, idempotency plays a big play in how you can cache HTTP objects safely. And E-tags are basically the GUIDs. E-tags end up as these fingerprints of like particular objects and a point in time snapshot of that particular object and so on. And so to achieve idempotency, the HTTP protocol has, the reason it gets so complicated is because when you start introducing caching or like another system on top of this, I'll go through an example. You start to have to reason about, okay, here's my version of the object. What's your version of the object? How are they the same? Do I have it already? If I have it already, I don't need to do anything. If they've changed, I need to know, and so on. And so you get these patterns in the HTTP protocol where like every object has an E tag, and you can do these like if none match requests and so on, where you can like ask a cache, here's all the E tags I know about for this object. Is your copy the same as one of those? And if it is, I'm not going to bother downloading it, and so on, right? Which is another crazy kind of idempotence. Anyway, back to our simpler example. So we've got a pretty basic system now of how to achieve what idempotency is and how to achieve it in a distributed system, right? We make a request, we give it a GUID, we send it to a server, we have the server record that GUID in some kind of ACID way, and if a repeat comes in, we just make sure the server, when it's serving requests, checks whether that GUID's there already, and if it is, don't do anything, and ideally just return the same response you would have, right? So that's nice and straightforward. But let's talk through, let's make it a little bit more complicated and try to get into why it gets hard to solve this when you start adding 3, 4, 5 more systems, right? Like, or in general, why if you add more components to a distributed system, this problem only gets harder and harder, right? And to do that, we're going to go through the example of, like, let's imagine we tried to build an idempotency service, right? Let's say, you know, hey, we've got regular services back here, right? Like web services, and we don't want them all to have to do this GUID pattern. That's a pain, right? Let's try to do it for them. So imagine we've got a service here like API Gateway, right? And let's say we just want to add a feature to API Gateway that's like, you know, API, we're just going to solve your idempotency challenges, right? We're gonna take that over for you, so you don't have to anymore. This would be a great feature for API Gateway, right? Like right up its street. Its job is to make it simpler for, you know, customers to build APIs, right? So why not solve idempotency for them while we're at it, right? So imagine we did this, right? So imagine, okay, well, the clients still generate GUIDs, right? And it goes to API Gateway. An API Gateway, when it sees it, it goes, okay, I'm gonna look in my store for that GUID, and if it happened already, I'm not even gonna send the request to the server, right? Well, straight away the first problem then is, okay, well, how do I know what kind of response to give in that case? I'm kind of really only left with the option of returning errors, right? So it straight away kind of limits you to the pattern of the less good pattern that I mentioned, right? We can only return an error in that case and tell them that, hey, this request was processed already. Still, that might be worth it for the feature. Like, a lot of customers might be willing to make that trade-off and say, you know, in return for not having to build idempotency myself, I don't really care that a client is occasionally going to have to go through this little dance of getting an error and then going and have to make a read request to find out whatever it is they needed to find out, and so on, right? Like, that could be an okay trade-off. But a more serious problem is, okay, so the request makes it the API Gateway, and in the case where, let's say, it hasn't seen this GUID before, okay, well, it's going to forward it to the server. All right, great. And the server is going to send back a response, right? And then it's going to record it in its, like, little GUID database, right? And then it's going to send the okay response back to the client, right? Okay, but what if this failed? Or what? Well, okay, that's kind of okay because we're not going to have recorded the GUID. So that case actually doesn't matter. But what if this fails? Okay, so the request made it to the server, so the server did something, but this response never made it to API Gateway. So it doesn't know whether it really happened or not. Oh dear. So it doesn't know whether it can save that GUID or not. Right? So I hope you can see idempotency, it has to be hop by hop. You can't build it for a system. Right? Every system that talks to another system has to think about this. So when you've got proxies or deep dependency trees, every single layer, they're going to have to think about this problem, right? Now you can simplify things a bit. You can use the same GUID at each layer, right? You can have this GUID here go to API Gateway, which can be passed on to the server, which in turn can be passed on to some microservice it's depending on, and so on, right? And they can all use the same GUID in their own little data stores, but they each have to have their own that accompany any actions they're taking. Now, if the microservice is just some kind of translation layer, doesn't do anything stateful, doesn't record anything durable, doesn't matter, right? Because, like, okay, well, you can ignore idempotence because we'll just come in and do it again, right? So that's okay. But if it is taking any kind of durable or stateful actions, you need idempotence there, right? And that's why. So that's one reason about why things have to be hop by hop. And then another challenge with idempotence is, often, you've got these middle systems that are trying to do things on behalf of another system. So let's say we're adding a tagging feature into API Gateway. Imagine API Gateway could just manage tags for you, right? Imagine it could, when you put an object, there's a certain way to indicate this object should be tagged X, or Y, whatever the client wants, and API gateway records those tags, right? And then when it just tracks those tags, it stores them. They get to the server, and when the server responds to API gateway, it doesn't even know that the tags are there. But then when API gateway responds to the client, it can add the tags, enforce tags, and so on, right? So imagine tags live in like API gateway layer, and objects live in like the server layer. Well, that gets even harder, because it turns out idempotency isn't even enough to solve problems like that. Because then you'll run into problems like, okay, well, what if I created the tag in API gateway, but I didn't create the object? Well, now I've got this weird orphaned tag over here with no reference. And as far as the client's concerned, the object doesn't even exist yet. And then what if they change their mind and they no longer want to create that object, right? It's not safe to have that tag lying around, because what if they change the request and the next time it comes in, it's like, oh, I do want to create that object, but without that original tag, right? So you need a way to disambiguate between like that instantiation of an object and the second instantiation of an object, and it gets really complicated really, really fast, right? And this is why eventually, like whenever you need to do things like that are coupled, or really strong idempotence across multiple layers, you eventually end up needing to do distributed transactions, where you have to run like a multi-phase commit protocol across all these layers, or you have to do like Paxos or Raft or something like that across all these layers. And things get this is why distributed systems gets gnarly and detailed in those areas, just to kind of open your mind to it, and why it doesn't work out. Anyway, but for idempotence, or basic idempotence, we don't have to think about it too much already. We've pretty much got it, right? We know that clients have to give some kind of unique identifier to requests, or any request they'd like to be able to repeat, and anything they're talking to, each hop along the way that's making any stateful or durable changes based on that request, has to incorporate that GUID and has to prevent duplicates. If we want to get an idempotent system, they're in a very pure kind of philosophical or academic sense, true idempotence is actually impossible. There will be side effects of making a request 2 or 3 times that are not the same as if it had happened the first time, right? Simple examples are, there'll be twice the amount of requests in the logs, right? If it occurs the first time versus the second time, they'll have different object creation times, right? Like things like that, right? Those little side effects, from a very pedantic, philosophical, academic point of view, mean that the system isn't really truly idempotent. It's not like sending 2 requests has exactly the same effect as only sending the first. But you kind of have to wash them aside. Although I will say an important one to think about is, especially in a system that you have to threat model, is if you're building idempotence for security reasons, because you want to make sure messages can't be replayed by an attacker, right? You should remember that typically a throttling system isn't always idempotent itself, right? So if the message can be replayed millions of times, maybe it could still overwhelm a throttling system, right? Which is, and you have to think about that differently, right? So there are other solutions to that. So I'll stop there for now, right? There's not too much more to say about idempotence. Hopefully that all made it in. I'm gonna go over all the questions now in a second, and then see what I might have missed, or see what people have. But as I said at the beginning, I think it's a good way to think about things as an intro. It gives you that first taste of differing perspectives in distributed systems, and why partitions are hard, and how we solve and wrangle some of these things. All right, let's see. All right, so first comment I didn't address already is the Nitro Enclave talk. Someone's referencing that. That is now on YouTube, so you can go look at that anytime you want. By the way, I'm using hexadecimal numbering on the YouTube talks, so we'll see how that goes. This is OX9, so I don't think anybody's going to be confused, but the next one, we'll see. We'll see how that goes. Let's see. Oh yeah, when we were figuring out HTTP, it's true. People were using modems. It was those times. All right, so Santana Andres has a point that when servers are distributed, like, how do you know some other server didn't respond to things? So this is a fundamental constraint in some distributed systems, right? So this is why, like, we can have CDNs relatively easily. So that's a content distribution network, right? And that's like a globally distributed set of servers that can cache and serve content, right? And for the most part, we don't have to worry about idempotency on read-only systems, right? Reads are inherently idempotent, right? You're not making any state changes, and even if the object changes, all that's going to happen is you'll either get the latest copy or the one slightly before, and that's okay. That's called eventual consistency, right? And we know how to architect that, and we know how to build that. So it's very easy to distribute something that's read-only, right? And a CDN is a really great example, where we can have nodes in Australia and New Zealand and South Africa, and we can have nodes in Seattle and Portland and Vancouver, right? Literally as far away as possible from one another. It doesn't matter that there's slight disagreement at any point in time between all those nodes about what the latest copy of something might be, because the system's kind of built around that assumption, and everybody's okay with that. But it's pretty close to impossible to do it for write-only systems, right? If you want to have idempotence, and if you want to be able to, like, persist and store durable copies of objects, like, you pretty much have your servers, your nodes pretty much have to be close enough together that you can do meaningful transactions and figure out whether you've got a unique, thing like a GUID token and so on. You can kind of, like, try to architect above that. You can add a consensus layer above this. Systems like Spanner, right, attempt to do this, where you can run a consensus protocol on top to see, well, out of all your locations in the world, what's currently healthy? Do I need to flip between them or do anything like that? But at the same time, any individual write in general is being steered to, like, one particular place where you can have an ACID transaction that's going to, enforce the kind of uniqueness and so on that we've been talking about today. Because otherwise, if I can send a transaction to, like, Seattle and send a transaction to, like, Dublin at the same time, right? Those are best case like 40 milliseconds apart at the speed of light, right? So if they're happening in parallel, they have no way to check for mutual uniqueness that's, like, slow, that's faster than, like, 80 milliseconds, which is just too slow, right? Like, no one wants to wait 80 milliseconds for a request to get processed. So the speed of light and the size of Earth just gets in our way, right? So you've pretty much got no choice except to say, no, for this directory or this data collection, like, Dublin is the authoritative location for it, so it has to go to Dublin to be stored, or it has to go to Seattle to be stored, right? But only Seattle. And if I want to change my mind, right, I have to pause the system for at least 80 milliseconds to do any kind of flip, because I'll need some kind of signaling mechanism where it's like, look, you can't, like, you were writing to Dublin, I'm going to let it write to Seattle for soon, so you got to pause in Dublin for a bit and then let Seattle take over. And that always takes, there's two ways to do it. Either you can proxy the writes, but speed of light's going to kill you there too, or you can have a bit of a write pause, and that's kind of a fundamental constraint. Maybe we'll get into that in a separate talk someday about how that comes in and why it's such an early problem of its own. But that's why you don't have to worry too much about whether the other servers distributed responded to things, because you just can't do that in the first place. Although I've seen a few people try to architect their systems that way, and they just end up vulnerable to duplicates. It's there's just some basic laws of physics involved. So we'll see. We talked about GUIDs already. That's reminded me of something we didn't talk about, which I'm going to add another 10-minute section on now in a second. And do we typically handle the case where a repeat request comes in while the first one is still being processed? So we generally do have to serialize requests to the same object or whatever, right? So if you put to an S3 object and you put again to the same S3 object, and those are from your perspective happening in parallel, at some place in S3 those are actually being serialized, and they have to be, right, for the system to work and to have consistency. And that's true for databases, it's true for basically any durable storage system, or else you'll get chaos. From a computer science point of view, what two adjacent topics would I recommend to read about and learn more? Oh my god. Adjacent to idempotency, but I mean directly on from idempotency is caching and distributed transactions. That's where things get fun. Just start with looking at, say, a simple two-phase commit and why it's structured the way it is. We'll probably get into that here some other day. Santana's making the point that requests can also arrive out of order. Happens all the time. R2 can come in and then R1 comes in, even though the client's in it before. But maybe that request gets unjammed, in the network or whatever, and it's awake from the dead. And that you have to think about that case too. And so that's something I didn't mention, right? A terrible thing to use for idempotence is timestamps. I've seen people try to do that, where they just put a timestamp in the first request, and then they go, well, if the second request comes in and it's got a higher timestamp than the first one, then that's the duplicate, and so on. It's no, because exactly what Santana said. Sometimes the first request can come in after the second request from the server's perspective. There's actually a nice relationship between all of this and Einstein's general relativity, where the order of events is all a matter of perspective and where you are, and you kind of have to adapt to that thinking too when you're building large distributed systems. So anyway, I teased a 10-minute section that I forgot to talk about, so I'm going to blame my head cold, and I'll get to that. So we talked about GUIDs as a way to achieve idempotence, and it is the most practical technique, and is almost certainly what you should go to if you're building an API. That's the normal way to how to do it if you have to store a durable state. But there's another pattern too, which is to try to make the requests themselves naturally idempotent. And a way to do that is some data structures for storing persistent state kind of have that property very naturally. They tend not to be very agile. They tend to be kind of esoteric data structures, like CRDTs are a good example, right? So if you haven't heard of CRDTs, they're commutative relational data types, I think. I'm not completely confident about that order, to be honest. But it's and they're a whole other approach to idempotency and ordering, where the goal is we're going to use consistent replicated. I was just totally wrong. Consistent replicated data types. I always think the C stands for commutative or commutativity. No, apparently we're all wrong. They're conflict free. All right, there we go. But the great thing about CRDTs they're basically data structures or data types, where you can send your requests, like your writes, in any order, and you'll still get the same outcome, right? So that's what they promise, and most of them, as just a nice convenient side effect, are also generally tolerate duplicates. If you send the same request twice or 3 or 4 times, it won't matter. It won't make any difference. often that's because what they're doing under the hood is they're using sketches or sketch algorithms or other things like that that actually have unique identifiers baked into them in a deeper way in how they work, as though they're just kind of naturally deduplicating. But that's like a whole other approach of how to make a system tolerant. And there's some pretty cool systems out there that people have built on top of CRDTs. CRDTs are often used by like collaborative text editors, right? Like people when you got multiple people typing at the same time, but people have crappy internet at home, right? And who knows whose keystrokes are going to make it in when and so forth, right? You can't plan for perfect ordering, but they'll still come to the same result no matter what order. As long as everybody gets all the events eventually, they'll all have the same page in front of them, which is pretty cool. Now, how they actually resolve conflicts, if I typed this and you deleted it and then so forth and so forth, that's like a matter for their implementations. But it's still pretty cool. So that's a whole other way to do things. I'll just give you a really simple example of like writing to a sketch or a CRDT that maybe will prove to you that it is possible, which is I'm going to use the classic cliched data structure, a Bloom filter, right, which we haven't done. Used to be a very cliched interview question. My friend Joe bemoans that as many times as he's seen Bloom filters on an interview whiteboard, he's never seen them in production. I am fortunate enough they actually get to work on something where we do use Bloom filters in production. So, haha. But if you don't know what a Bloom filter is, they're really, really simple data structures. It's basically an array, right? So you've got an array with slots in it. And let's say all we can store in each slot in the array is a bit, a 0 or a 1, right? That is also called a bitmap, a map of bits, right? And those bitmaps, those 1-bit bitmaps that we've all seen of images and so on, that's all they are, just big arrays of zeros and ones, right? And the idea is, if you want to, so Bloom filters don't store objects, but they are things you can write to, and they record basically whether or not you've seen an object or not, right? And or maybe have seen an object. We'll see why that is in a bit. And the way you do it is really simple. You've got a Bloom filter of any size you want. You make it as big as you like. The bigger it is, the more effective it'll be, but obviously it'll cost you more memory. But you get to make that trade-off. So you can make, but it's not uncommon for a Bloom filter to be like a meg, like really big, like a lot of bits, right? So like 1 million of these bits, right? And then you take some kind of input and you put it through a hash function, right? So let's say I've got an object, I'll just use my name as an input, and you run a number of hash functions on it. You get to pick the number of hash functions. The more you do, again, up to a point, the more effective the Bloom filter will be. We'll see why. But obviously it costs you for every single one you add, you have to compute it. So let's say I'm going to use 3, right? So I'm going to run 3 different hash functions on my name. Now, when I say 3 different hash functions, what does that mean, right? Usually that means actually we're going to use the same hash algorithm 3 times, but with a different seed, right? Like in real world terms, this might turn into, SHA-256, literally the string 1 plus the input column, right? And this one's going to be the same, but with a different input, with 2 plus whatever, right? And effectively this part here, where we're doing like SHA-256, but always starting with 1, and then always starting with 2, that's a different hash function, because they'll produce different outputs, right? Even though they're getting the same input, my name in both cases, they'll just get radically different outputs, because that's what hash functions are. you can get a Twitch stream about it if you want to go see. So we do that 3 times, and we get 3 completely different outputs. And then we take that output, so here it's a 256-bit number, right? And we try and turn that into like one of these array indexes. Like, let's say there's 1 million of these, so we take 2 to the 256 and we mod it by 1 million, right? And that gives us a number between 0 and 1 million, right? That this will correspond to. So just for easiness sake, let's say that then hashes to like 3, and this hashes to like 7, and let's say we do it again, and hashes to like 5, 3, 5, and 7 are set to 1. And those are now recorded. That means this Bloom filter records that it saw the string column by setting these 3 bits. And the way you can see that this is idempotent is if I do this again, it's going to be the same 3 bits. Right? So if I send in another request, hey, record that you saw a column, it's going to do all of this, and it's going to get 3, 7, and 5 again. And it's just going to set these 3 bits. So whether the first requester is processed or not, by the end of the second, we'll still have bits 3, 5, and 7 set, no matter what. So it's naturally idempotent. Just to explain the rest of Bloom filters, since we're here, let's say we have another string. I'm going to pick Santana because I see his name in the comments. And we do the same thing here, and it comes to bits, let's say 3, 4, and 8, then I'm going to set, 3 is set already, so don't do anything. Now I'm going to set 4, and I'm going to set 8, right? And the Bloom filter kind of fills up over time. Now in reality, I'm going to have 1 million of these bits, right? So it's not going to be too dense. I'm going to have lots of slots that are zeros. And then the way a Bloom filter works is, to test if you saw a string or not, we go through this process again, and then we check if the bits are set, right? And if I come in with, yep, those 3 bits are set, so we probably saw a column. And if I do this again for Santana, it's going to be like, yep, we probably saw Santana because his 3 bits are set. Now if I come in with a totally different string, let's just pick Eve, and that goes to like 2 and 1 and 3, bits 1 and 2 aren't set, so we definitely didn't see Eve. So Bloom filters can tell you for sure that you didn't see something, and they can tell you probably saw something. And the reason you say probably is because, there is some chance that like other things came along and set those bits by chance, and then that's why we're saying we probably saw a column. But that part doesn't matter. But for the idempotency purposes, just remember that like as far as this goes as a sketch algorithm, it's naturally idempotent, right? And there are indexes and other things. Hyperlog logs have a similar behavior, right? So there are other approaches than just setting GUIDs. If you want to get into much more advanced, data types. All right. What is the correct pronunciation of my name? Oh man, my parents say it different from each other. So good luck with that. I say Cullum, which most people can't really say. There's kind of slight vowel sounds in there that come from the Irish language that just don't seem to come naturally to people, and it doesn't bother me at all what people say. We have other vowel sounds in Irish too that just are extremely unfamiliar to English speakers. Loch is a pretty classic one. Like people know Loch, and some people can say it, especially Dutch and South African people. But then we have like an RH sound, at the end of the word car, and there's a difference between car and car in Irish, and there's a difference between Cullum and column, which you probably couldn't even hear, or at least a lot of people tell me they can't even hear. But those are, when I say Cullum and I say column, most people in Ireland can tell those two apart by quite a way, and actually would use them in different contexts. Another unusual thing about the Irish language is your name is pronounced differently and spelled differently depending on the context. Like it can be column, hullum, whillum. That's the nominative case. If somebody was just saying, "Hey, Cullum," like they would say "Ach, Willum," which is completely different again, right? So, it like all of this is a long way to say it really does not matter how to say it, because there is no one way to say it. It's Irish is a crazy language. Well, welcome to the party. So there you go. Awesome. Newfoundland here. I love Come From Away. Seen it several times. Great musical. Go see it. Seriously, people, if you've never seen Come From Away, even if you don't like musicals, give it a try. It's on I think it's on Apple TV now, if you want to watch it. And friends of mine are in the band, so that's double the reason to go watch it. All right. I think that's everything for Idempotency. If you've any other questions, take them to Twitter. As I said at the beginning, all the talks are now up on YouTube. Just go look for the Shuffle Sharding channel, or go to my website shufflesharding.com and just click on the videos or YouTube icon, and you'll get a link right there. So the full archive is up, and hopefully this will be up pretty soon. And this will be OX9, and I'll have this up within a day or two on YouTube, although it'll live on Twitch for the next 16 days. Thanks again. If you've thoughts on what I should do next week, out of meetings and soft skills for meetings is the top contender at the moment. But if you think I should do shuffle sharding or something else, let me know. Anyway, stay well, everybody.